Hello, everyone, and welcome to our next session. This session will be led by Aamir Aftab. He is the Senior Technical Lead at Chevron. So if you'll please join me in welcoming him to the stage, he will take it away now.
Thank you, Jessica. Hi, everyone. I'm going to share my screen. So today's talk is about the predictive analytics for multi-phase flow in oil and gas forecasting. So one of the major things that we need in order to increase the maximum objective value of an oil field is to employ strategies that would help with the maximum benefit. And so we have certain types of completion techniques, such as the two ones are smart and conventional. The smart work completion technique is basically where they install permanent downhole gauges in the well for monitoring well integrity, the pressure, temperature sensors, and can do regulation as well. It's a very, it has a lot of sensors and valves. However, due to the economic uncertainty and the cost of developing a smart well completion and doing the smart completion is high, it's a lot of the oil and gas wells in the world are using the conventional techniques, which do not have those kind of sensors. And so we have to come up with a strategy or a way where we can help the production optimization using temporal data. And in order to do that, we need surveillance and optimization. So surveillance and optimization is whereby we can increase the ROI of the and profitability of an oil field. It has it produces techniques for field production optimization, letting us know cost per barrel of oil reduction and quantification of workover remedial operations. So this surveillance analysis and production optimization is actually these tools are highly complex. And in order to do that, we need to come up with strategies. So some of the things that we're going to cover today are the types of measurements that are used in the in the temporal data. So pressure is really important, temperature, and we are going to talk about flowing bottom hole pressure. So the flowing bottom hole pressure is where the production engineer can actually design the production objectivity index and find out that basically if they perform certain work, or if a certain type of an artificial lift is installed, how much improvement will it be from the existing performance. So for these purposes, to create these models, the production engineers need flowing bottom hole pressure. And so since a lot of the wells are conventional, and also the smart wells themselves require high maintenance, and and the pressure gauges or the permanent downhole gauges that are installed or go bad due to the harsh reservoir environment, and and the maximum lifespan for them is maybe like 10 years. So really, like smart or conventional, we need the ability for us to predict the flowing bottom hole pressure. So that's one of the problems that I was talking about earlier, where these smart well completion require permanent downhole gauges for collaboration and maintenance, and they go bad due to scaling, corrosion, malfunctioning, and as well as in order to get the bottom hole pressure from a conventional completion perspective, the well has to be put has to be put on hold, and it's basically due to this interruption. It has, when it's off production, it leads to economic losses. So it's not going to be very often that they're going to go and shut down the well and then do the test. So temporal data, we use data-driven models to predict FBHV. One of the sources that I used was this scientific petroleum engineer, so from the Society of Petroleum Engineers portal. It's the real-time prognosis of flowing bottom hole pressure in vertical well, which is the talk. So I got this table from their paper, and I saw that the data wasn't, there was a lot of data gaps. Like they said it's 206 points, but actually, they only show maybe 8 points. So for my study, this talk, I should say, I took the descriptive statistics data from their data set, which they provided in their paper. And I thought, what if I was to, take the mean, the standard deviation, and use the most simplest approach of Excel, inverse normal distribution, and generate 206 points, random points from this data for all these temporal, data attributes, which are basically independent variables for our dependent variable, which is flowing bottom hole pressure. For them, they actually have split their data set into a training data set and a testing data set. So 70% of the data they are keeping in their training data set, and 30% is actually for their testing purposes. So this is the the chart that is showing us the correlation coefficient between flowing bottom hole pressure and all these temporal data sets. So we can see that the the depth and the oil rate and the water rate are are closely related, correlated with the have a positive effect with the flowing bottom hole pressure. Meanwhile, the the tubing diameter is indirectly related. And so I took as I was talking about, I took that data and I decided to build my own model. So this model, using from the data set that I created from those descriptive statistics, I decided to use that as a way for me to generate my data set and see if the methodology, results, keeping all other factors outside, if it would, correlate, the values will correlate with what they said in the paper. But yet that wasn't the case. I used Pearson correlation coefficient, which they did in the paper as well. And I came up with the correlation of FBHP versus all these different, independent data sets. But they don't match because, for instance, depth is closely related to it in positive effect. But in my data set, it's actually an inverse. So same as that with the water rate, the oil rate. Even though oil rate is a little bit much better using mean and standard deviation for filling up the data quality gaps, it's the depth is absolutely outside of the distribution for us. And then the third important one is wellhead pressure, and that is basically correlated. Some of the more functions I did, like comparisons, to see if I could use the kurtosis and make it closely related to the table, the value that they had in their table. But it did not it did not match at all. And so this leads to the point that we need machine learning to help us with, using maybe neural networks or nodal analysis for the just, to create, the possibilities for being as close as possible to the real-time flowing bottom hole prediction. And so mean and standard deviations, although are the quickest, did not fulfill this, this study at all. So, that was one of the things. But in order to achieve, this machine learning aspect, we have a solution for this problem. And basically, the solution is to use what I was showing over here, the notebooks in my Visual Studio Code, which run on the Azure Database platform, that allows us to run our ETLs, transform data, have models that would basically keep training and giving the observation. So this can be thought of as a SCADA sensors that are sending in pressure and water injection data, which are then used through these different stages to go to the transformation logic on Databricks, and then can be loaded in the data warehouse or the data lake. So going inside the Databricks aspect of it, as I was saying, like when this ingestion is done, so we can use Azure Data Factory to perform this ingestion, and then push that data to Databricks platform where it can run the notebooks and the basically perform the training data, as well as give us the results as well. So here are the references that I used for my talk. And any questions? So some of the other things that we did was also find out the distribution of it. So a lot of this interactive notebook functionality of Jupyter notebooks is really good because it can give you on-demand analysis, and we have used it a lot in a lot of my work for saltwater disposal wells. Performing analysis on the on the pressure and injection, and seeing if the saltwater well is actually going through some fracturing or plugging, and then providing the reservoir engineer and the the geophysicist the understanding of the well. Again, this is the data set. The X is basically the matrix of features. And I'm using that to basically build my independent variables and the dependent variable. Yeah, and so the way I was missing values from the inverse normal distribution function that I used in Excel was I used a simple imputer to impute and transform or interpolate for those values that were missing in the data set. Still, even after filling the missing values, the correlation wasn't matching. I did, I split the data set into test and training results as well. and both of them were off from the study. Another thing to point out is that this is not at all one dimensional. There are a lot of physics associated with the pressure data that's coming in from the sensors because of the properties of the reservoir, how tight the rock formation is, as well as the surface level properties. Even though I'm not a subject matter expert in petroleum engineering, it's a passion. So that's why it's a very very interesting and very complex field. But so this is like machine learning is the key to helping us solve those problems due to the economic uncertainty that happens as well. You have to maximize your revenue and your productivity. Another thing that I'm going to point out over here is that the Jupyter notebooks themselves, this project I can deploy using DevOps, Azure DevOps to the Databricks environment. So we can build an end-to-end deployment, continuous integration and continuous deployment of our machine learning code, as well as the transformation logic, which I was showing over here. This is the ETL that happens in this solution to solve the data quality and data gaps issue that's happening. Going back to the correlation coefficient. So the random, there's no normal distribution, which is of course like using mean and standard deviation, we can do that, but in reality, the result set is much different. But we can have multiple notebooks that and data models that can run parallel and can give us the prediction for that flowing bottom hole pressure. Because this solution is extremely scalable, so it can increase the amount of computation it needs if there's a lot of data coming in. And can scale itself down because it's a platform as a service. So when the sensor data starts coming in, it scales up and does the transformation. And of course, if their sensors are not on, or for example, the well is offline, then the clusters can switch off and can be can stay that way until the well comes back online. So this is one of the graphs that I got from the Society of Petroleum Engineers. It basically showing the productivity in productive injectivity, the improvement in the performance. So, for example, over here for the production engineers trying to understand if a certain remedial workover is going to provide more improvement. Or let's say if another type of artificial lift system needs to be installed in order to increase the flow rate, for example, ESP or gas lift. And all those those simulations have to be done and before the in the design completion design as well. So this graph and these properties then allow the production engineer the ability to do that. One of the other things that I wanted to point out as well in this solution is that you have the training models and the the jobs that are running side by side. So once your training data is your training data or your notebooks are doing the calculations, these jobs can be run on an event trigger, or they can be run on a scheduler. Basically, an event trigger could be such that for example, the production engineer can come in and change the well properties. And then on changing those well properties, the system can then use those independent variables to predict the simulation. And for that, the event trigger which will run the notebook. Meanwhile, if there's a scheduled job, then when the data starts flowing in for a daily average, then these notebooks can perform the calculations and incrementally add the simulation data to the database and the result set. And this is not only installing on Azure Database. Can also run a virtual machine and using Kubernetes and have this Spark environment set up. That does have a bit of an overhead because of the maintenance and management of that environment. However, Azure has Azure Kubernetes services where they take care of the maintenance and the management and the administration of the cluster. And we can use those nodes or pods to deploy our microservices as well as our Docker containers, which hold a Spark environment with for our data science and analytics. This data can also be mimicked by once this machine learning functionality is implemented, then a lot of forecasting in the future for that independent data can be done as well. Due to this study, my data set using the traditional, more quick approach did not match. And so that shows that this is a very complex and it has a lot of parameters and a lot of physics involved in these measurements, which need to be accounted for in our equations and on our algorithms, and that's where machine learning can greatly help us achieve that result. So it's not as quick and easy as using the min maximum. That was one of the steps I took, or using mean and standard deviation for that. The mean was close for 206 data points, but the correlation coefficient wasn't. So it didn't look like it was distributed properly. mean, of course, in the real world scenario, you would have data sets from your well, uh, so that they would be available. So mm, proving this technique would be much more easier than because I was trying to do an extra step of or extra steps I should say for finding out the gaps in the data and trying to interpolate that because there is a huge gap and there are very few data points. That's the hurdle that I found in my calculations which I did in my Jupyter notebooks. Although using that data that was generated, this might be uh, this numerically this might make sense because of the calculations, but in actuality it's way different due to the the environments and the properties of all the different various layers in well completion. You can also run this your Jupyter notebooks locally on your machine, and I used Anaconda distribution. So this is me running a local cluster and running my notebooks on there. So this gives us the ability to debug and perform our our analysis locally. Although Databricks does allow interactive notebooks, but that actually defeats the purpose of CI/CD because if everyone is working on itself on the Databricks side, then it becomes difficult to maintain. And I think that concludes my talk.